All right. So firstly, a couple of things. The way I wanted to do this is I'm not an expert in this field by any stretch of the imagination. So I'm trying to learn it too. Okay, along. So hopefully we'll all learn together. That's the first thing. But as usual, as with any other talk or session that I do, have any question, feel free to interrupt me right in the middle. Okay, and ask me. You don't need to wait till the end and all. That's not required. Number two, I've tried to make it for software engineers. So even though maybe the first 10-15 minutes we'll talk a little bit about the quantum phenomena, but very quickly we'll get into the computational model that you and I can use instead of talking too much about theory, because that will probably not work as well. Yeah. So those are the sort of conditions under which we're going to have this. And let's see, I may not be able to complete this whole thing today. If I can't, then we'll have another session, because I definitely don't want to run beyond 50 minutes to an hour. Yeah, because there are other things we need to, I think we all have other things to do in our day. Okay. So what will we cover as part of this lecture or this talk or whatever? Few things. We'll talk a little bit about the double slit experiment. Unfortunately or fortunately, we need to do that. It'll not be right to talk about quantum computation without talking about the double slit experiment. Then we will get into our familiar area with linear algebra. Believe it or not, even within quantum mechanics, you cannot escape linear algebra. It's still going to be vectors and matrices and tensors and all of that. Yeah, Ramya, come in. Yeah. And then we'll probably talk a little bit about qubits and superposition and things like that. I'll probably start talking about it and then we'll figure out, guys. Sorry for this. Right, so we're talking a little bit about the double slit experiment. Then we'll get into some computation with how do you do with, Cbits and qubits and things like that. We'll also talk about superposition and some basic quantum logic. It's not dates, it's gates. It's written there as logic dates, it's logic gates. So we'll talk about some basic logic gates. We'll also talk about a simple problem where a quantum computer actually beats classical computers. So, at the end of the day, it's all good to talk about quantum computing, but why bother about it, right? The whole idea is there are certain sets of problems where quantum computers will outperform classical computers. So we'll talk a little bit about that. And I just thought it will not be right for me to leave you guys without talking a little bit about quantum entanglement and teleportation and things like that, right? Which are just some bonus topics. If we have some time at the end, I'll talk about it. And depending on our interest levels, we can see how deep we want to talk about some of these things. Yeah, we are actually not going to be doing much of algorithm development. I wanted to do some base coding, but I could not set up that Microsoft's Q# language in time. I think it's having some problems there. At least today, I was not able to do it. That's why we'll not probably do some coding today, but let's see if everything works out. The next session I take, we'll actually try and do some coding in some language like Q#, right? Q# is Microsoft's quantum computing language. Okay. All right, so I think everybody has seen this slide before in their life at some point or not, right? This is the whole Moore's law, that the computation doubles every 18 months, right? All of you are familiar with this, right? Everybody has seen this, and this is something that that has been going on over the last 30-40 years at least. And the reason we kind of talking about this slide right now is if you look at the latest chipsets, right, which are like the Apple M1, for example, or the latest Intel chips, or the one from Qualcomm, the whole Snapdragon series, you're talking about more than 12 to 16 to 18 billion ICs, on one chip. So it's getting extremely dense. So the whole point is when it gets this dense, you start getting into other problems that you normally don't get into, right? And we won't talk about this in detail, but there is a theorem, and people who probably come from some physics background, more specifically around electromechanical systems and heat systems and things like that. You'd have heard about something called the Newman-Landau limit. Okay, I don't know how many people remember that, but there's a limit which basically says if you want to perform a non-reversible operation. Okay, most of the operations that we perform are actually non-reversible operations. There is a minimum energy threshold. The minimum energy that will be required to perform those is given by your Newman-Landau limit. The problem is when this much energy gets used, heat gets generated. And the whole problem is how to take away this heat from systems like this and all of that, right? So it becomes a big problem. So you start getting into quantum mechanical type issues. So I think we're not yet there, but we are pretty close. So maybe it's estimated that within the next decade, your classical computers will start hitting the Newman-Landau limit, and at which point you will have to talk about quantum computers any which way. Okay. All right. So that's just to give you some context. Right. So I'm sure everybody has this question. If you don't have, you should have it, right? Even classical computers are based on transistors and ICs, which follow quantum mechanics, right? But are based on classical logic. So what is so special about quantum computers? Why should you care about quantum computers? Can anybody tell me when all of you decided to come and listen to this talk from me, why did you want to do it? What did you guys think was special about quantum computers? It's okay, man. I'm not going to mark you guys on anything. You can just say whatever. No, silence is dangerous, especially in remote. I'm getting irritated with this. I just feel like I'm talking to myself nowadays in most of these classes. So just tell me, anybody, anything. I see a lot of people. I'll start calling you by names then.
Increasing the computational speed or of
Yes.
solving the intractable solutions.
Correct. So you used a pair of very key words there, which we will probably get in back a little later. So intractable problems, and you can solve it much faster. So two words you said. I think I would suggest everybody remember those two words. We'll come back to them. Yes. Anything else?
Hey, Srini. I'm thinking probably maybe in the domain of probabilistic programming, given key qubits have a characteristic of staying in multiple states at one point, versus the more transistor based where you can be either 0 or 1, the bit based. So again, all of these are pure guesses. I believe the probabilistic side of programming could be faster on quantum computers. Should be faster.
Yes, that's one thing, but faster how? I think you're getting close to it. Faster how? Why will it get faster?
Uh, Probably so in normal bit based, at any point of the time, one state is either in 0 or 1. But in just one state can be in multiple positions based on anything which will get into entanglements. So I'm believing with one bit, we will be able to store much more data versus the more with one qubit, we would be able to store much more data compared to one bits. Maybe somehow that leads to.
You started off well. Unfortunately, this is not right. Okay.
Okay.
What you can store with a qubit is essentially the same that you store with a classical bit. But I'll give you a hint. Parallelism.
So Srini, in the past world, this was more of a distributed computing where the work used to get distributed across the, till past 5 years or so, we had the core distribution at the processor level. Now at the processor level, again the distribution is come down to a chip level where the chips are made such fine and with so much power that we don't have to go with a breadth of processors, but the same processor can do what multiple processors used to do in the past. So the computing power is increasing at a processor level and at a processor level within the chip also. The ICs that are coming together today, they are able to do what a single processor used to do in the past.
I think all of you are getting close, but you're not really kind of giving the answer. But yes, I understand the sentiment at that level. Unfortunately, yeah, you're all right. But this is a technology sort of a class, or a lecture, so things have to be precise. But yes, it's to do with speed. And it's to do with, and the reason why we think they'll be faster is because they're going to be parallel. But end of the day, even classical computers have parallelism, right? We do parallelism even with classical computing. How do we do that? We take up a problem, break it in, and then feed those instructions to CPUs in parallel. And then we sort of this is the parallelism that we talk about in the classical world, right? That's how you do, right? You take a problem, break it into sets, into instructions, and then feed those instructions in parallel to different CPUs, and finally you kind of recombine all of them to give you the one answer. The difference between parallelism in the classical and in the quantum world is in the quantum world, parallelism is inherent. And we'll see what I mean when I say that. You don't have to break an instruction set into smaller instruction set and feed into different processor units in parallel and then recombine them. The way the processing happens itself is inherently parallel. And part of it, somebody alluded to things being in multiple states and entanglement and things like that. So superposition and entanglement are some reasons, not the entire reasons though, but are some reasons. But at the end of the day, a qubit in itself, a quantum bit, is just like a classical bit, still just holds one bit of information. So that doesn't, but how you do operations on qubits is what is different, and you can achieve some inherent parallelism. And we will see part of this. This is an introductory class, but we will still see how to do some of those in some basic quantum gates and things like that. Let me move on. Okay, so I don't think there are a few people I'll pay homage to before I start this because that's just the way they deserve to be paid homage to. So I think most people should recognize this person. At least if you are interested in physics, you should definitely know. He's Richard Feynman. Richard Feynman's lectures. I remember buying that book in second store bookstalls way back when I was a kid. Fantastic book. If you haven't read lectures of Feynman, I think you should. I think everybody should. Okay, this guy was an absolute genius. And in '82 was when he actually said that can we actually simulate physics on a classical computer? Because most physics is quantum mechanical at this point. So how do you simulate quantum mechanical systems on a computer? This was the fundamental question that he asked, which has led to pretty much all the development that we talk about today in terms of using quantum computing. Because really, if you think about laws of physics, ideally we should be able to use laws of physics to cure diseases, right? If somebody's from bio, you should be able to do it because finally all diseases will be quantum mechanical in nature. They should obey the laws of physics. But today we can't. We can't because the laws that we apply there are just way too complex to be applied here. We just don't have the compute. We just don't have a way to come, because if you could, then you could pretty much solve any problem. Okay, because the laws of physics are immutable at that level, right? Whether it is a living thing or a non-living thing, it's not like you have different laws of physics. The laws of physics are exactly the same. So things should work, but they don't, and because we can't compute them, that was the spirit in which he has this question. Okay, so this is not to delve into too much detail, just to understand there's a person called Richard Feynman. There is another person I'm going to pay homage to before I move on. This guy was in 1500s. Okay, most of you may not have heard about him, unfortunately. His name is Giraldo Cardoni. Okay, he was Italian, part of the Renaissance and things like that. The reason why I want to pay home to remember this guy before we get into quantum computing is fundamentally there are two things that we use in quantum computing. Okay, that you got to be aware of, which is probability and complex numbers. Basically, two concepts that are very important. And this guy, at least it is the first written mention of both were by this guy. And this was in 1500s, close to 100 years before even Pascal, okay, 100 years before Newton. So it is fascinating, okay, what this guy did. He was a gambler, he was a degenerate, he died before he was 25, but he pretty much did whatever he needed to do. So he was interested in probability because he was a gambler. Most people who were interested in probability back in the day were gamblers. They want to understand what was going on and things like that. And he was interested in complex numbers for a very, very strange reason. he was somehow obsessed with finding the roots of cubic polynomials. He was doing a lot of work around that. And if you read his book, it will be strange. He was fascinated with square root of minus 15 for some reason. Okay, we don't really know why, but he was the first guy that we know who had written the square root of a negative number and was trying to work with it, right? And he actually writes in his book that you can do a lot of things with it. You can do addition, you can do subtraction, you can do multiplication, but it all still seems nonsensical because they are square roots of negative numbers. So we don't know what it means, but the math actually works. Uh, Unfortunately, he didn't get his place in history, but there'll be many such people who will not get their place in history, but he was a fantastic guy. And a little bit about probability again, if you really, okay, see, I won't get into too much of discussion about probability per se, but if you really understand probability, there are at least two lines of thought, right? Till the last century, which was a lot of people said probability is just a subjective thing, right? It depends on your belief. If I ask you what is the probability of something coming up, it depends on your belief. If you believe that, if I say what is the probability of getting a 6 on the roll of a dice, it depends on your belief system. You can say, hey, I believe that the dice is fair. I believe that the guy who's rolling the dice is fair. So if you believe all of this, you will come to one answer. Otherwise, you'll come to some other answer. So probability is very subjective in that sense. There were another set of people like Karl Popper and others who kind of fought about it and said, no, it is actually objective. Probability, you can actually calculate probabilities, and probabilities actually make sense and all of that. And this was for like what, 300-400 years. There was a fight that was going on. Then there was a guy called Kolmogorov, okay, and this is important for you to know as I get along into double slit experiment. Kolmogorov was a 20th century mathematician, early 1900s, Russian guy. Okay, he was typical like a mathematician. Okay, he just said, I don't care about your philosophies, all of your nonsense. You're just wasting time. Okay, he said, I'm just going to define 3 axioms. Anything that follows these 3 axioms is a probability. Period. There is no, I'm not going to debate on anything. So he just said, probability is something that is a non-negative number. Okay, he simply said it has to be a non-negative number. Then he said, the probability of something that is certain to happen is always going to be 1. Okay. These 2 are sort of trivial axioms. The third one is critical. He says, if 2 events are mutually exclusive, the probability of them occurring is just an addition of their probabilities. So for example, if you roll a dice and if you say what is the probability of getting an even number, there can be 2, 4, and 6 are even numbers. So what he essentially said, it just means is the probability of 2 plus probability of 4 plus probability of 6 will give you the probability of an even number. Again, for us, it sounds trivial, but it's very important. In quantum physics, we will end up breaking this assumption. Okay, this is the assumption that we will break. That's the whole difference between the from a mathematic. If you ask a mathematician, the only difference between the classical world and the quantum world is we break this assumption of Kolmogorov. Okay, this assumption of Kolmogorov is broken. Right? Yeah, Samir, necessity is the mother of invention. Probability for gambling. Yes, absolutely. Yes, probability, and that's the whole frequentist probability that you talk about. But yes, you're right. So that's the thing, right? And we'll talk about how that's broken in the subsequent slides. But I wanted to tell you some key people in this field before we move on. Right, slight digression. We got to take central problem in quantum physics again, like what Richard Feynman said, the double slit experiment. We'll talk about the double slit experiment. We will not understand it. Nobody has understood it, but I will go through it to tell you what that experiment is. Yeah? If you understand it, that's it, man. I don't even know what to call you. You have solved the universe and everything else along with it. Okay, nobody understands the double slit experiment, but we'll go through it because it's unfair to go through quantum computing without understanding double slit. Okay, fantastic, fine. So this is a simple experiment, right? You have some light source, you have 2 slits, and you see some bands on the other side, right? If you put a detector, simple diffraction, right? Light behaves like a wave. Light behaves like a wave, it diffracts, and you see that nothing phenomenal. Newton knew about this. Okay, so everybody knew about this. We all have studied theories around this, reflection, refraction, your formulae, all of this you studied based on this, right? Now, let us say if you believe that light is a particle, which is the wave particle duality of light that you kind of learn. If it's a particle and if there are two slits and you pour them through it, I'm just giving an example of sand here because you don't have photons falling, but you do that, then this is how you will expect them to be kind of grouped together, right? With some probabilities. Again, in the classical world, you kind of put some sand and you do that. Now we're getting into the interesting setup. Okay. So now let's just say we have something with two slits. Okay. You've covered one slit. You just have one slit open, and you're now shooting, let's say, photons. They can be atoms, they can be electrons, they can be photons, they can be any ions. All of them, neutrinos, protons, they'll all behave similarly. Okay. So, but anything that is at a quantum level is what you're talking about. Okay. If you throw balls, it won't work like this. It has to be at quantum level. You do this, and if you kind of put a detector on the other screen and you try and detect what goes on, that's how you'll detect it, right? One band with some dispersion, which you are hoping is because things are bouncing off things or whatever. So there is some slight dispersion, but there is one clear band, right? Now you open the other slit and you see what happens. Now this is nonsense, right? Because you get a wave-like pattern when you're shooting particles. How does that happen? Photons are particles. So when you're shooting atoms or photons, how are they giving you the same pattern? This is the same pattern like what would have come if you hit a wave, right? It's kind of the same sort of diffraction pattern that you're seeing here. So this is the this is the issue, right? We don't know. We don't know what is going on because maybe the force could be. Yeah, we'll get into a lot of assumptions like that. Don't worry. There are a billion assumptions on why that happens. Okay, but we'll see some more interesting things. Now, if you're a physicist or if you're a scientist, you want to do different things, right? What do you want to do? You want to now hit them probably particle by particle and see what's going on exactly, right? Because that's the scientist in us, which is trying to kind of make you do things like that. So if you do that, if you're kind of looking at particle by particle, it still forms the same thing. Like you see every particle passing through these slits, but the pattern at the end will be a wave-like pattern. It still does this, but we are still not very convinced, right? We are horrible people. Humans want to understand exactly what is going on because it doesn't make sense. Your entire physics just falls apart. Your Kolmogorov's third axiom falls apart. What is the probability of them happening there? It should be if the probability of a particle passing through the first slit is, let's say, P1. And let's say if the probability of it passing through the slit 2 is P2. And both of them are mutually exclusive, right? Because a particle either passes through slit 1 or through slit 2. Then the probability of it landing it anywhere else should be P1 plus P2. That's what Kolmogorov says. That's how we built our entire bloody statistics and probability based on that. But that is not P1 plus P2. That is something else. Who knows what that is? Yeah, no. We are detecting photons on the other side. We are not detecting air. That's a pattern that's formed. You can do it in vacuum. You can do it in all sorts of things. That doesn't matter. Okay. So now what do? We actually put a detector on just one slit. Okay, on just one slit we put a detector. On the other slit we are not detecting. I am just saying I am going to detect it as it is moving through. Okay, I am detecting. Here also I am detecting, and then I am seeing the thing at the end. What do I see now? Now I see only two points, which is probably closer to classical probability, or what you would assume. So what the hell? Does the photon know that it's being spied upon? I don't know, right? You remove the detector, you again see the same pattern. Like I said, nobody understands the double slit experiment, but this is what goes on in a double slit experiment. We will talk a little later in this talk on why that happens, okay? On why something like that happens and how do you mathematically explain such a phenomenon. But the important thing at this point for you to remember is Kolmogorov's third axiom is broken. Okay, And that's a very, very important part. So probability, as you knew about it, doesn't. Yes, and you how to decide. Yes.
So maybe that light, when you put the camera, that light is deviating the photons or not.
Wave particle dual nature of light.
That's what.
Particle
Duality, but duality is somehow it is seeming to decide when to be a particle and when to be a wave.
Yeah.
And even within particles, it is deciding. See, how is it knowing that something else is passing through the other thing, and hence I will adjust to look like this at the other end? Correct. When this is happening, what is it doing? It is deciding to form a specific. But it doesn't make sense, right? A photon you don't think has consciousness to kind of make these sort of decisions en route. Anyway, don't get too carried away with this. There are a lot of the answer is in entanglement. Okay.
Maybe that electricity that's coming from there that is creating a magnetic field.
All of that is measured, Shrikant. It's not like you are having phenomena out there that you can't observe. Okay? We know it. The whole point is anyway. That's fine. So we'll get about it. We'll talk about it. It's up to quantum entanglement when we get to entanglement, but we'll focus on the computation model a little bit, so that because we actually want to be practical about it, and then we will also talk about this. The strange part is Einstein felt exactly like you, so you are not in inferior company. Okay, when this came out, Einstein was completely against it. He thought this is all nonsense, that this can't work out. And actually Einstein with two of his colleagues, it's called the EPR, Einstein, Polotowski, and Rosen. Three people together. It's called the EPR. Okay. Three of them created a paradox, again, which we'll talk a little later, and they called it the EPR paradox, to say if this was how the world would be, then this is how stupid they have to behave. And I think it is the EPR paradox, right? But the real tragedy is when later on, when scientists did those experiments, they figured out that quantum systems exactly behave the way the EPR paradox wanted them to behave. So even though Einstein and we all think it's all stupid, that is how the universe actually seems to behave. So which is the joke, which is the actual. It's as if nature played a joke. Okay. Anyway, two powerful ideas. We've got quantum complexity and quantum error correction that we'll go through. Quantum complexity, I think we talked about a little bit, but the idea that I want to bring it there is high amount of parallelism because of entanglement and because of superposition and all of that. But the real problem, the thing why we can't achieve that so easily, we have to also understand, we have to be very, very clear about that this is not a solved problem. Okay. The problem is, if you have a quantum system, think about you have a quantum system, right? And you're trying to do some computation in the quantum system. Then, every time the quantum system reacts with its world nearby, the quantum state changes. So there will be errors included, like errors will keep propagating through the system. So it's very, very difficult to create an isolated quantum system that can actually work and do your computation without being affected by its external environment. So you have to do something called quantum error correction. A lot of error correction needs to happen. And typically for one qubit that has to work properly, you may have to have about from 5 to 10 qubits. You have to just kind of put them as redundant qubits just for managing the error correction. Though we will not be going into those details as part of this lecture, but that's a huge problem, right? And there is a certain mathematical, there is a whole field of mathematicians who believe that quantum computing will never even happen. Okay, not at the scale that we want, and that's something that you guys need to be aware of before you want to spend the rest of your life doing it. That's because the whole idea is as you increase qubits, the noise within those qubits grows exponentially. So it's not a race you can win. I'll be very sad if that happens, because that means as if the universe is conspiring against you and not letting you give you that compute. But there is a whole theory around it. Okay, but at this point, at least for the sort of quantum computers we are creating, we are able to create. Of course, we are creating much smaller ones, just about 100 qubits sort of size at this point. But at those sizes, we are able to do it. Can we do it over a million qubit size? We don't know. The answer is we just don't know. We may be able to get there in the next decade. We may never be able to get there. Okay, but anyway. Moving on. Okay, now
I
now.
think with the light brains are working, we don't be able to achieve because our brain also kind of sending waves, I believe.
Yeah,
So we also have some kind of frequencies, So that will affect your quantum field.
yes. I don't know.
That's my understanding.
Yeah, I don't know about that. I don't want to go in there. But this is the reason, right? Now, this is the reason why we want to do quantum computing, right? What we believe is there are some classically easy problems. You heard about that. You guys familiar with PNP type thing? Okay, I'll just give you a 10-second thing of this. There are certain problems that we think are easily solvable. When I say easy, can be solved in polynomial time. Right? What is polynomial time? Some polynomial where the worst case scenario, if you look at some sorting algorithm, for example, or some search algorithm, or those sort of algorithms have worst case time bounds, which are polynomial in nature. Polynomial means some x to the power 5, x to the power n type bounds. Okay. Now, now there are another set of problems which we call non-polynomial deterministic. So, for example, if I give you a problem, now those problems do not have a solution in polynomial time, but given a solution, you can see if it's right or wrong in polynomial time. So, for example, if you take Sudoku, Sudoku it is impossible for you to write an algorithm that solves a Sudoku of any size, of size n by n, where n tends to infinity, in polynomial time. You can't do that. Okay, it's not possible. But given a solution, you can see if it's the right solution or not in polynomial time. That you can do. For example, the same factorization problem that you talk about, right? Given a large number, all your security, all your RSA security, everything is based on prime factorization. Given a large prime number, can you factorize it? Yeah, hi. Can you factorize it? Now, factorization cannot be done in polynomial time. There is no algorithm to do. If you could do it, then there is no security in the world. Because all security, all RSA encryption is based on the simple assumption that primes cannot be factored in polynomial time, large primes. But given two numbers, you can easily multiply them and see if it's a solution or not. Right? So there are certain problems which can be solved in polynomial time. There are certain problems that cannot be solved in non-polynomial time, but the solution can be fitted. You can see the solution or not in non-polynomial deterministic time. That is NP. Then there's a third class of problems which I will quickly go through, which is called non-polynomial complete, NP complete problems. Okay, sorry. The NP complete problems are such that where you cannot even check the solution in polynomial time. Forget about solving it in polynomial time. You cannot even check the solution in polynomial time. Okay. Traveling salesman problem, for example. For certain classes of traveling salesman problem, you cannot solve the problem in P. Given a solution, you cannot even determine if it is the best solution in using in P time. So it is NP complete. Okay. So those sort of problems. And of course, there's a whole thing about P equals NP and all of that. But that just means that if you solve one NP problem, you can solve all of them. There's an equivalence or a homeomorphism out there. And this is the dream we have got in quantum computing. That what you have, I don't know why this is becoming like this, but hopefully, yeah. So, yeah. So there are certain problems which are classically easy, which we say are P, and hopefully it also includes some NP problems, which are NP in the classical sense, but become classically easy in the quantum sense. And some are quantumly easy, which we are hoping is the whole class of NP complete. And quantumly hard, at this point, our guess is hopefully there is nothing there. But that's just a guess, okay? It's a Millennium Prize. Nobody really knows about it. I'm sure there are problems that are even quantumly hard. But that's the idea, right? That's the big idea why we are chasing this dream. Okay, so one more person that I want to, from now on, there's a guy called David Mellman. He's David Mellman. He's a Nobel Prize winner. He's a physicist. He's one of the pioneers in quantum physics. And there is a class that he taught at UC Berkeley, and where he said, shut up and calculate. Okay, say you cannot understand quantum physics. Don't try and get scenarios in your classical world to match up there, because our language is not sufficient. Our language itself is modeled in the classical world. The words that I use don't make sense in the quantum world. So the only guidepost that you've got in this world is mathematics. Mathematics is the only thing that works. So, and I completely agree with his opinion on this. Shut up and calculate. Whatever your equation tells you is the answer. Okay, it is not like, hey, this is the quantum world. It looks, this is similar to this in the classical world. No, it's not similar. It cannot be similar. Even the word similar doesn't mean anything. So we shouldn't be using all that. Yeah, yeah. I have always read his lectures. I've always followed him. You can also do it. He's a fantastic physicist from UC Berkeley. Okay. All right. Now we come into, I think, the real part of what engineers will be interested in, because we'll be starting to solve some problems here. From till now it was English. We get to the math now. So right. So now let's just say, forget about quantum thing now for a while, okay? It's got nothing to do with quantum. So a normal classical bit, if you've got a classical bit can have the values of 0 or 1, okay? That's all the values that it can have. So the way you write 0 is that you see that weird notation, you know, with some greater than symbol and then a line on the left-hand side. That's known as the Dirac notation. After Paul Dirac. I think everybody should have heard about Paul Dirac. It's also called the light ray notation and things like that. He's a physicist. Paul Dirac notation. But we will use the below notation to simplify it, because if I had used that notation, first learning that notation would be more you know, cumbersome for people. Okay. So you write 0 like the one I write on the top. So think about it as an array indexed from 0. So if you have 1 at the 0th position, that basically means it's 0. Okay, 1 at the 1th position means it's 1. That's it. Okay, 1 0 0 1, simple, right? And you will be very, very familiar by the time I'm done with this class. You know, this will be second nature to you guys. If it's not, then anyway you're lost. So it should be, right? Simple. This is just a very, very simple revision of matrix and multiplications. Yeah, I don't really want to go through it too much. I just hope you guys know, but I just want to put it out there saying that, hey, don't tell me how you multiply 2 matrices or 2 vectors or whatever. So that is what that is. Okay, it's nothing great. Nothing great. I would like to take your attention though to those matrices on the matrix on the right side. Okay, so you see that matrix which has got ones on the diagonal and 0 everywhere else. What is special about it?
Identity matrix.
Is the identity matrix, right? So because if you multiply with that, you get the same value back. Now the one below is a little interesting, right? What is the difference between the one below and the one up? The third and fourth rows are reversed, ulta, right? The third and the fourth rows are reversed. Correct?
Yes.
No, the second and the third row, sorry. The second and the third row. The second and the second row comes below and the third row goes up. Right? The second and the third rows are mixed up. So what happens if you multiply it with 0, 1, 0, 0, you get 0, 0, 1, 0. So those two numbers also flip. So whatever rows you are flipping, the numbers there in that column flip. Okay, it's an important intuition to have, because you will keep doing it so many times that it's just a trick. Instead of having to multiply the whole thing, you multiply the whole thing, you'll get the same result any which way. It's just for you to remember that trick. Okay, makes sense, guys? Till here, there is nothing. I don't think I've said anything which is great. Okay, I should have probably asked this question to you guys before, but I forgot. So when you have 1 bit, you can do 4 operations on 1 bit. Correct? With 1 bit, you can, and this has got nothing to do with quantum. It's classical also, you can do only 4 operations if you have 1 bit. What are those? They can be an identity operation. Okay. Negation, opposite, constant 0, constant 1, which means irrespective of whatever the input is, you make it into a 0. Irrespective of whatever the operation is, you make it into a 1. Right? 4 operations: identity, negation, constant 0, constant 1. Okay. Now here there is a bit of question on what is a reversible operation and what is an irreversible operation. Let's talk about that a little bit. So always remember those matrices on the left side. Okay. The reason I'm telling you that is it's so important. See, identity, diagonal 1 1. When you say negation, 1, 1, opposite. Diagonal is 0, 0. Okay. When you say constant 0, all zeros have ones. The top one, 1, 1, 0, 0. Constant 1, ulta. 0, 0, 1, 1. It's just for you to remember. Yeah, you don't have to memorize it today now, but I think as you go through this, you'll probably understand. But now let us talk a little bit about what is a reversible operation and what is an irreversible operation. Reversible operation basically means looking at the output and the operator, I should be able to get what the input was. Irreversible operation is one where you cannot do that. Now, is identity a reversible operation? Yes, identity is a reversible operation. Is negation a reversible operation? Why?
No, yes.
Yes, no, because it's just reverse. If you know what the input was reverse. If you see the output and if you know it's a negation, then you know that then the input was the opposite. And guys, on the phone, you can also speak up, okay? That's why I wanted people in a room. It's far more easier for me to kind of communicate. But anyway, constant 0, is that reversible?
No, it's always 0.
Correct. Constant 0 is not reversible. Similarly, constant 1 is not reversible. Now, in quantum computing, all operations are reversible. And we'll see how to do these constant zeros and constant ones in our quantum world. In quantum world, every operation needs to be only reversible. What is the reason for that? I hinted at the reason with the Newman-Landau limit. Because otherwise, it needs energy. Quantum states do not take in external energy. If you live in a quantum state, they change on their own. So it's a reversible operation. Otherwise, you will hit the Newman-Landau. That's why that's an important theorem when you talk about quantum computing.
In the Tenet movie, did they apply the same?
Where?
Tenet movie.
I haven't seen that movie actually. Tenet. Yeah, I have.
That whole movie talks about quantum.
Oh wow, maybe I should see it then. I haven't.
They actually reverse the life to backwards, and then there is a.
Yeah, but time travel is not possible even in the quantum. Teleportation is possible, and we can talk about it later.
Ant-Man, they do this.
Yeah, in movies, they are not, like Mark Twain said, no, truth is not limited by fiction. In fiction, you're at least limited by your imagination. Truth isn't. So in quantum mechanics, you're not limited. Anyway, let's move on. So you understand that, right? Constant 0, constant 1, reversible, irreversible. Reversible means that given the operation and the output value, you can find the input value. Okay. Operations which permute are reversible. Operations which erase and overwrite are not. Right? Because identity doesn't permute anything. Negation just flips. Okay. Constant 0 and constant 1 overwrites. Hence, you cannot. Okay. Identity. Quantum computers use only reversible operations, so we will care only about those. The important thing is the bottom line. In fact, all quantum operations are not only reversible, they are also their inverses. Right? For identity and negation, it's simple, right? You take 0, 1, you apply negation, it becomes 1, 0. You again apply negation, it becomes 0, 1. So all quantum operators are not only reversible, they are also their own inverses. And these are very, very important theorems. But till now it's all clear, right, for everybody. There is no problem anywhere. Now I'm going to talk about something else which you may or may not have seen depending on if you are a triple E major or not. Okay, it's called the tensor product of vectors. In electricity, probably they should teach. I don't know if they teach in undergrad or maybe in postgrad. Intermediate also. You have tensor product of vectors? Okay, fantastic. So this is the tensor product of vectors. It's not very simple, right? It's depicted with that circle with that x in it. Okay, you have two vectors x0 and y0, x0 x1, y0 y1. It is basically, it will have 4 x0 y0 x0 y1, x1 y0 x1 y1. So even with 3, it's the same repetition. Okay. This is called if these two, if x0, x1 and y0, y1 can be taken as two bits, two classical bits, right? Then the tensor product can be taken as the state of those two vectors, of those two bits, of those two classical bits. I'm still not going to talk at a quantum bit because we have not arrived at a quantum bit. But it doesn't matter. The concept is exactly same. Okay. So it's not very difficult, right? You can just do that multiplication. Tensor product of vectors is again important. It's a simple enough concept. Just remember it. Okay. Yeah, exactly. If you're trying to represent, now we are trying to start seeing about representing multiple classical bits, right? If it's 0 0 1 0 1 0, it will be 1 followed by 3 zeros. So, and this Dirac notation, slowly start getting a little bit used to it. It's not, because it's a much easier notation to do, right? And you understand why that is 4, right? If I can write it as 4 also. You understand? Because 1 0 0 in binary is 4. Yeah?
Yes.
Sorry?
No, I'm saying I got it.
Okay, good. Yeah, so it's nothing very, yeah. Siddharth, okay, Siddharth. So it's simple. So that's why it's 4. We call this tensor representation the product state, right? Or the vector state. Some people will call it vector state or product state, doesn't matter. We can factor the product state back into the individual state representation. This is very, very important. So given the vector state, the product state, because I'm going to call it product state here, you can factor it out. Now, the question that you might have is it always possible to factor it out? Okay. The answer is no. Right now, we will talk about, for a while, we will pretend as if it is always possible. There will come a stage when I'll start talking about quantum entanglement, where we will see that those product state cannot always be factored out. In fact, that can be the mathematical definition of what is an entanglement. The product state of two qubits cannot be factored out. Okay, but anyway, I'm putting the horse before, or the cart before the horse right now, I guess. But the product state of n bits is a vector of size 2n, right?
Yes.
And here there is a small whisper you can probably hear of the power of quantum computing, that parallelism that you're talking about, right? It's 2 to the power n. So if you have n qubits, you will have a, and using things like superposition, you can do some fun things. Okay, so, and that's where the sort of it's still a gentle whisper, but I'm hoping you can hear it as we get along. You'll probably see it a little bit more. Okay, so till now, okay, guys, everybody fine with whatever I said?
I remember there is another principle 2 power n minus 1, so I don't know what it is.
There are so many things. So which is
This switching theory and logic.
oh yes, yeah, there is. Yeah, we'll. Okay, now this is a very, very important operation in quantum computing. Okay, it is called control knot, C knot. C stands for control. Okay, so in classical computing, and we can learn it using classical theory, but we will probably use it in the quantum computing more. But see, in classical chip design or logic gate design, more than chip design, you know that you can do everything using NAND gates, right? So that's what the theory is. Anybody who's a computer science engineer should definitely know. Anybody who isn't also, who has taken some courses on logic theory and things like that, should know. So your basic gate is called the NAND gate, and using a combination of NAND gates, you can build pretty much every other gate, whether it's the OR gate or the AND gate or the XOR gate or whatever gate that we are talking about in classical computing, you can build using NAND gates, right? So that's the whole funda. Similarly, we can build the C naught gate is the base gate for quantum computing. Okay, again, not 100% true. This whole thing that I'm talking about. If you really go out in the market, talk about it is called the Gates quantum computation model. Okay, this whole model that I'm talking about. There are other quantum computation models also. I think one is after a guy named Tomophil. Okay, Tomosil or Tomophil. I forgot his name. Okay, so there is another model after him and things like that, where the C0 gate is not enough. There are other gates also that come in, but in the computation model that we are going to be talking about today, because this is the more simpler introductory one, the C0 becomes very, very important. So how do you understand C0 gate operates? This operates on pair of bits now. So on one bit, you had 4 operations. Okay. Now this is a gate that operates on, because it's a gate, you would want this gate to operate on 2 bits. Okay. It operates on a pair of bits. Now you have to call one of it as a control bit and the other as a target bit. If the control bit is 1, then the target bit is flipped. If the control bit is 0, the target bit is unchanged. That's the logic. Control not is that. Okay. The control bit is always unchanged. So if you pass in 0, 0, you should get 0, 0. If you pass in 0, 1, you should get 0, 1. But if you pass 1, 0, you should get 1, 1. And if you pass 1, 1, you should get 1, 0. Because the control bit is 1, the target bit is flipped. And the most significant bit is always the control bit. Okay. The most significant bit is the control bit. Control bit is 1, the target bit is flipped. So that is the gate. Because the last 2 things will flip. If you flip the last 2 rows, that matrix that you see is the C0 gate simply. That is, maybe it is a homework for you guys to go back and see that multiplying with that matrix will always give you what you are expecting here. And see, it's always useful to try out these things, because otherwise it's like my son learning mathematics only. It's completely useless. So you can't read a lecture and learn. You have to do it. Unfortunately, there is no shorter way. Okay, I keep telling it to everybody. These are some examples. I think you can just go through it. See, if you don't understand it, ask me, because it's very simple. I think it's nearly 12 o'clock. So probably we'll have to arrange. Maybe looking at my pace, we'll probably have to do 2 more sessions for me to complete this. But that's good, because I think whatever you learn, it's better that you learn properly rather than me breezing through these slides, which I could have done, but that's of no value either to me or to you. Okay. So, and that, how do we factor it out from this to into this? Right now, let's not get into that. Okay. You only validate up to this point. How this is becoming the other one is a separate story. Factoring it out. Factoring out the product states is something that we will see as part of quantum entanglement. Okay, that's where you will see. But right now, let's just believe me on that. But look at till this, because that is important. Okay. Okay, last 2-3 minutes, I'll take some questions. I'll just see what's the next slide. Operations on. Oh, it's just more and more examples. Maybe I can show this also. There's no problem. It's just more examples. And I will send the deck up to this point. The reason I don't want to send the whole deck is I don't want you coming into the class completely confused, and then me having to, because those slides don't explain everything. They just put whatever I wanted to put out there, right? So it doesn't explain everything. Okay, anything last 2-3 minutes, 4 minutes, you have some questions for me or whatever, or also feedback for me. I'm open to feedback, because the next class that I take, I can change myself to make it more useful for you guys. So, because please understand, this is for you, this is not for me. Fortunately or unfortunately, I have done this a couple of years ago, so I am okay.
So why this quantum computing is very important? Why?
Because we believe, like I said, that those NP problems that we in classical computing think cannot be solved in polynomial deterministic time. We think that quantum computing will offer us the speed up to be able to solve some of those problems. Can we or can't we? Still, the jury is out. Because there is a millennium, I don't know if you guys, there's actually called a Millennium Prize in Mathematics. It was announced in the year 2000 by the Cray Institute. About 7 mathematical problems, they said. Anybody who solves this in this millennium, they will pay $1 million for each. Okay. Out of the 7, just 1 got knocked off. The Poincare conjecture, right? The Poincare conjecture, I don't know if you guys know about it. The Poincare conjecture got knocked off in 2015. It's a mathematician who proved the Poincare conjecture and got his $1 million. But the other 6 are still remaining, and this is one of those 6 where you're saying, can all NP problems, is P equals NP? See, when I say non-polynomial deterministic, it can be because of 2 reasons, right? Because inherently the problem is very, very difficult and cannot be solved, or we don't have the tools to solve it, or we don't have the algorithms to solve it, right? If we build the tools and the algorithms, then all of those problems become solvable. So that's what the proof is. Whether it is a tool problem or there is some intrinsic hardness of the problem that does not lend it to be solved in polynomial time. Okay. The big idea is quantum mechanics lets you do that, and also it lets you, to what Richard Feynman's point, lets you simulate quantum mechanical systems. What that means is, next time there is a disease like corona or COVID-19, you can pretty much immediately find a cure for it, because you can simulate the entire human body and all the cell interactions and everything else, the entire quantum mechanical systems on a computer. So the solution is instantaneous, right? There is no need for anything. You can just instantaneously know that, hey, exactly is what happening. This is the equation to solve. You solve the equation and you get the answer. That's it. So that's the world we hopefully will get to at some point. Right now, we're not there yet. Of course, we see we're not there yet. We are suffering. So, but that's the idea. So once you do that, all quantum mechanical systems can be simulated. Today we can't. Today anything. I don't know if you guys are interested in physics. There's a 3-body problem. You can't solve the 3-body problem, right? Today, there is no analytical solution just for, if you have the Earth, the Sun, and the Moon. Just take 3 bodies in the solar system. Take all of their initial positions and all of their forces acting on it. You cannot analytically solve that problem to tell me where exactly each one of these things will be X years later. You can't analytically solve it. Even the 3-body problem is not solvable today. Okay, you can simulate it. You have numerical approximations, but you cannot analytically solve it. So even a 3-body problem we can't solve today. So we are at a pretty pathetic state like that. Even though after all our so-called advancements in math, we still struggle. Okay, but anyway, it's good to understand, and hopefully this was useful. Any other feedback from guys on the phone, please?